computer. Okay, everyone. So today, after this, you will have course from Professor Beka Taskinen. Also, tomorrow you will have the course from him still, and then me about the fundamental of metallurgical process. And after that, Associate Professor Longgong will tell about the application of thermodynamic. And then Peka, if you know the biggest copper smelting using double flash smelting, single line, the biggest now in Indonesia, in Freeport, in Gresik, and PK is one of the developer of the technology. So you will learn from the developer of the double flash smelting and also the copper smelting technology in general. And after that, we have Professor Zulhan. From him, you will learn about how to process nickel from nickel laterite. As you know, Indonesia is the biggest nickel resource in the world. And after that, you will have Professor Zaki teaching you about the hydrometallurgical process of nickel laterite, and then Dr. Zela about high pressure acid leaching, and then Dr. Nurul Zahalim about coal downstream technology. And on 22 of August, you will have Prof. Su Kaihua. He is from industry also from Central South University about production of material for battery. And after that, you will have Dr. Wira about rare earth. And then from industry, you will have Dr. Arif Tirto Aji to tell about the progress maybe of the Manyar project, the biggest double flash copper smelter single line in the world. And then you will have again Associate Professor Sia Longgong to tell about the production of zinc and lead, and then recycling in China, and then we have a bacterial thing, biome hydrometallurgy from Professor Siti Khotijah, and in September we will have Professor Mali Lundström. She is the leading professor in battery from Finland, and after that we have Professor Daniel Lindberg. If you have fake sets, you will see his name in fake sets. Professor Daniel Lindberg will tell us about the thermodynamic applications for metallurgical industry, for example. And we will have Associate Professor Edi Sanwani about separation using a physical principle for primary and secondary resources. And then we will have Dr. Taufik Hidayat for the last session. So this will be very interesting courses. So please don't miss it, everyone. So you will have credit for ITB student. You will have credit. You have to attend 70% of the class, and for international student, you will have credit also. The credit can be transferred to your original university. And the course, in order to get credit, you have to attend at least 70% of attendance, and you have to write literature review, minimum 3,000 words. The topic of the essay is recent development of technological review for metal productions. So for ITB students, for example, it can be the chapter 1 of your final bachelor thesis. So it can be chapter 1, because in chapter 1, if you write a final thesis, bachelor thesis, you have to write like a review. All the material, all the link will be submitted in EduNext system, including your final assignment. You have to submit in EduNext. We will explain later on via WhatsApp how to access EduNext system of ITB. Because you already enroll, it is automatically you have right to access the EduNext system. So this is the example of the writing, the essay. You will get these materials. And yes, that's from me as the coordinator of the course. Any questions? from all participants. Okay? If you have a question, you can directly ask from WhatsApp, for example. Okay, everyone? Pekka, are you still here?
Yes, I'm here.
Yes. Yes. Okay, everyone. Professor Pekka Taskinen will give you the first lecture of this process metallurgical, of this sustainable process metallurgy. Pekka, time is yours.
Thank you, Imam. Can you see my screen?
Yes, very clearly.
Good. So these two lectures, today and tomorrow, I have divided them into two parts with an idea that this first lecture is about general issues of sustainability. And the second, tomorrow's lecture, is about sustainability in metals production. What has been done and what has been achieved during those say 100 years of time when all these problems started. I mean, over kind of consuming of the resources of the earth. But let's proceed. Yes. As we know, metals are produced from ores and concentrates, which have been generated over the very, very long periods of time in geological processes, and they are, in practice at least, finite. If we knew ways of digging more deeply in the Earth's crust, we could increase our potential to get these metals, but in the end, our metal resources are finite. At some point, they are excavated. They are ending. The other very important issue here is that extraction of these minerals, ores, and smelting metals from these minerals needs energy, and that energy today is mostly coming from non-renewable sources, which is changing rapidly in at least in some parts of the world. So we are moving towards solar and wind power and not increasing carbon dioxide content of the atmosphere anymore. So some metal producers are even today introducing carbon zero metals, which have been produced with full electrified mines and without any fossil fuels in the smelting. And that is coming more and more common in the years to come. But the situation in general is that because mineral resources are finite, metal making can never be sustainable as such. So it is clear that at some point we are exhausting our primary resources of minerals for making metals. And because of this, we need to secure the availability of metals by recycling those end-of-life goods containing metals. And this is something we all societies, or most societies in the world are looking at least, and some are even exercising. So to improve availability and reduce the environmental burden, these are the two big issues in this field. And as I mentioned, so the availability of metals is one issue, but the excessive use of fossil fuels, coke, coal, and oil, sometimes also natural gas. They are causing global warming, and that must be stopped. I have a special slide as the last slide of today's lecture about this, which shows the kind of dangerous situation we are facing today. What is then causing this increased demand of metals? It is simply the growing population of the world. And what we see, luckily, is that many nations, most nations, are also increasing the growth of their gross national product, meaning that they are becoming wealthier. Sometimes at low rate, sometimes at higher rate, but that is a general thing, general trend, and that means that people have more possibilities of buying goods, which most likely include also metal parts. But then there is this real megatrend, which is kind of swinging the pendulum in the in the other side, it is it is the general trend of making everything smaller. So I call it miniaturization, and it is something you don't see easily, but you need to look at the time spans of 50 or 100 years. Think about cars 100 years ago. They were heavy, they were not so powerful, and their kind of engineering level was low. But nowadays, our cars are much lighter, and their kind of capabilities of carrying load and people are much better than this first Ford car, which revolutionized the world in 1920s. The same has happened with cell phones. Nokia, which is not a cell phone producer today, they launched their first portable cell phone in late 80s, and it was like a shoebox. Its weight was probably 5 kilos or something, and it was really portable, but you couldn't squeeze it in your pocket. Nowadays, cell phones are perhaps 100-gram weight, and their capabilities are completely different from that Nokia's first cell phone. So that is miniaturization. Everything is packed into smaller space. All components are smaller, so less metal, less resources in general, which also has some some negative features, but that's not the topic of my today's lecture. So how in a very general sketch, so to say, metals are produced. We have today primary metals production, which is ore extraction, concentration. These are taking place in mine site, and then smelting. And the same is practically used in secondary metals production, where these end-of-life goods are coming to kind of market. So municipalities collect them in one way or other, and these are typically mechanical operations. So shredding, sorting into various fractions, plastics, metals, and metals further on to steels and and non-ferrous metals, and non-ferrous metals further on to aluminium, lead, and copper. And then at some point these fractions are going to to secondary smelting, which may be also part of the primary smelting today, and it is often so in Europe at least. And this step produces a relatively pure copper, lead, zinc, also iron for steel making and so on. And then this actual downstream processing, which is starting from component manufacturing. Those components are assembled in products. Products are sent to retail, and then that product is consumed. And this, which is one of the main messages of mine today, is roughly the circular economy of metals. So we like to do metals consumption in wide wide perspective, in such a way that those consumed goods which can be reused, they will be reused here. And if there is something which can be modified for reuse, so this route directs the end of life goods to product manufacturer, and then back to sales and consumption, and it may be even totally remanufactured, so that it's end use is something else that used to be here. And as the last option, so to say, is this recycling, which is very much the issue of coming generations and legislation in countries, because if we don't have rules which are binding, which are compulsory to follow, so this kind of system doesn't work. What has happened with metals and their use over the last about 300, 400 years is that in addition to the increased demand of metals, also more metals have been taken into let's say practical use. So in in old ages, some 300 years ago, we didn't have more than copper and iron, tin, zinc, and lead. So 5 metals plus carbon in use. 100 years later, it was 3 more. So cobalt, manganese were used in large quantities. And then 100 years ago, it was really tripled or more. So early 20th century, we had such metals as aluminium, tungsten, molybdenum, titanium, also nickel in use in technical and engineering purposes. And some 20 years ago, the palette was much more. So there was things like uranium, bismuth, zirconium. So that means that these old metals we used to consume in 300 to 300 years ago, we know how to utilize them, and we know how, in many cases, we now know the engineering skills to recycle them, as has been long time in copper and iron making the case. But we have had since more than 100 years now metals which are belonging to so-called minority metals, which are available at relatively small quantities in the earth. And also they may be available in such a way that like copper, it is rather evenly distributed over the countries. But chromium, for example, most chromium resources are probably in 2 or 3 countries only. So there is a kind of geographical geographically uneven distribution of those small metals. Chromium, molybdenum, platinum, group metals in general, and perhaps also nickel. So shall we, in the coming years, shall we take more metals into use? Nobody knows, but it is evident, I would say. I wouldn't expect any kind of smaller number of metals used in the future compared to this very year. as I said earlier, this metals production in general is very much in general linked with energy. And that energy is actually contained in the price of each metal. So that means that metals are never end products. Their value is up to demand, and they are commodities. They are traded between companies who have them and who don't have them, who need them. And this is somewhat old but still valid graphics about the use of basic metal goods in the world. And you can see that two major areas are very important here. So this manufacturing of electronics, machinery and equipment, which is the biggest consumer of metals, and construction, so housing, roads, bridges, and then we have smaller consumers of basic metal goods, which is actually quite amazing. Manufacture fabricated metal products, so things which are used as such is coming third, and transport equipment is amazingly big as well, fourth. But then if we look at the energy used by industry, so mining and quarrying is by far the biggest user of energy in the world. And then we have two other sectors which are perhaps 1/4 or 1/3 of this mining area, and third is coke making and refined petroleum, so oil refinery industry, and second is all equipment needed for electricity, gas, steam, and air conditioning supply. So, as I said, when metal making is at some day not profitable anymore to a smelter or refinery, the energy is typically that thing which is ruining the profitability. And that is why many metal making companies are doing rather rough decisions when electricity price, coal price, coke price go up, and they can't get the profits from their metal products because of the expensive raw materials. How European Union has tackling this shortage of metals, evident shortage of metals, is really this phrase, circular economy. European Union has been estimating a few years ago that only 10% of goods is cycled back into the use in one way or other, and out of those extracted 92.8 gigatons, whatever that is, so about third is totally wasted, and more than 50% is dispersed or emitted. Dispersed meaning it is mixed with other waste materials at so low concentrations that they cannot be recovered. And there we see this need of legislation and processes making the circularity possible. The current, still in many places, available or used system is linear economy, and it means that after use, after the point of end of life, these goods are in one way or other, they are wasted, landfilled, or just forgotten in the corner of your garage. One example is my home here in close to Aalto campus, some 15 kilometers west of Helsinki. Ten years ago, perhaps a bit more, we got new waste bins in our backyard. There is 7 different bins which are kind of separated by the people living in this housing department. So there is certainly glass and metal, and then there is plastics, paper, cardboard, and bio waste, which goes to composting. And then 7th is what is the 7th? Yeah, it is that fraction which used to be the biggest one in the past. So it's general waste which goes to incineration, and it used to be more than 50% of my waste fractions before this new system came. And now it is perhaps 10%. So waste to energy is one way of utilizing energy resources of waste, but it is not with a high priority. So in that sense, this is legal system in Finland, and those metal goods are going into recycling companies, and glass, I think it's going to glass making and so on. So the concept of circular economy is quite simple. So we have these extraction industries, including farming, producing primary raw materials to processing plants. Those processing plants may take byproducts from other industries, like typically, as I said, copper scrap has been smelted in as a routine basis in copper smelters. Always, I would say. But also other things like various copper-containing sludges and materials coming from in small quantities from other industries, dyes and that kind of things. So this processing step is where we have our kind of responsibility, and it gets, as shown earlier, it gets its recycled components from the end of the usability step or period, and this should be only the last option for effectively using the metal values of the products. So sharing and maintenance is the most wanted, reuse and redistribute. So going to the sales or organizations, shops. Second one, and then remanufacturing the last before recycling. And EU has estimated that up to 25–30% of primary raw materials production can be replaced by this kind of controlled end of life system, and it would mean quite nice reduction in use of mineral resources consumption as well. To generalize this circular economy, and in order to explain that it's not only metals making, which is the industry of concern, this EU's kind of sketch or two-sided picture of the circular economy is also emphasizing the farming industry, which has significant values in terms of products like biochemical feedstocks, biogas, and then also biofuels. So this is a concept, circular economy, which is not characteristically part of metal making at all. If you look at the Finnish power production, we have a lot of pulp and paper industry like Indonesia has. And our bio-based electric energy counts about 40% of the total. So that means that parts of the processing residues are combusted in pulp and paper industry, and those pulp and paper companies actually are very big power generating companies as well. The big issue here is actually the collection of end-of-life goods, which needs legislation on national and international level. And that legislation must set measures, responsibilities, and incentives for following these concepts and its details. And it is really easy to understand why on a voluntary basis this doesn't work. So if you buy a battery from a shop, what will you do with that when it's flat, when it's gone, it's dead? You probably put it in somewhere in your home and forget it. The same with used laptops, cell phones, and so on. This is a big challenge to countries, and it is the key for this circular economy, key for this more effective use of metals and resources in general. But there are, in EU, European Union, there are also rather strict regulations to the consumer products. So since 2006, lead-free solders were a must in EU. So you couldn't sell a single electronic kind of equipment if it contained lead as soldering material after 2006. And also the more recent design for recycling concept has been taken into use. So that means that you should, as a manufacturer, you should provide such products which are allowing that scrapyard operation, where the different components of different materials are easily broken down, and their kind of complexity must be less. So this year, even Apple agreed to have this USB-C connector in their cell phone in Europe, because they were the last one who didn't accept that requirement. And EU probably would have stopped sales of Apple cell phones and probably other goods in Europe if they didn't agree. So now we don't have to have 2 or 3 transformers and charging wires for cell phones, as it was earlier the case. And that also increases the resource efficiency. If we look the circular economy in more detail, so the Ellen MacArthur Foundation defines this as an economy that is restorative by design, which aims to keep products, components, and materials at their highest utility and value at all times. So here is now few more this energy recovery, which means that incineration of general waste in my country, and also this top prevention, which means that you should use your cell phone not half a year, but 4 or 5 years preferably, which may be difficult to some people. Yes. What has happened with the demand of metals over a rather small time span is shown here. So copper, aluminium, steel, their demand has been increasing on the average all the time. there are downs and ups, like after that 2008 economic crisis, aluminium was also going down, but on the average, all metals are needed more and more. This period from probably 1995 to 2000 or 2001 was very hard time to many metal makers, because then the price of energy used in metal making was higher than the value of the metal. Many companies so disrupted, stopped their production for a while, 1 year, 2 years. And actually the latest news from Australia, what I have seen, they say that is happening again with nickel. But after 2001, the demand has been growing much in all aluminium, steel, and copper. And this is the, if you look at trends for individual metals over much longer period of time, so they are the same. Not actually the same, but similar. So this growth or demand will not cease. When you are now as a student of this field, looking at long trends, this is copper production, copper mine production, which is always somewhat less than copper production because of this recycling. So you must understand what this increase in demand means. We have copper and aluminium, perhaps, are metals which are used very much in heavy investment goods, and their lifetime is in many cases more than 50 years. So if we put copper into national grid now, it's available for recycling perhaps after 70 years, sometimes more than 100 years. That means that metal is not available for recycling. And this is the case with many metals. Steel, cities have tall buildings which are designed with because they are high, their height is substantial. They are designed to resist all the stress and strain by steel constructions. Those buildings in Europe, they may be more than 100 years old. And that means that steel which is in there is not available for recycling. And here is a good example. I plotted this vertical line here to point out the year 1975, which is about 50 years from now. And
Apa aja jadinya benefitnya? Yang platinum.
Sorry. If that copper which was produced 1975, it was a bit more than 6 million tons only. When the present production is mine production is 22 or something, and total production is 25 or 26. So if 50% of that copper, that about 6 million tons, comes to recycling today, it's 3 million tons, and it's only less than 15% of today's demand. So that explains why the recycling rate in copper industry never can be very high because of the way and end use of copper. Yes, this graph shows United Nations prediction of the world population, or predictions, and it would, if the average of that set of curves would be the most likely. So it means that 75 years from now, we have about 11 billion people on the planet, when the present is 8. So it's declining. So the derivative of that curve is declining, not the absolute number, even if some forecasts propose a maximum before 2100. So that means that that it's almost 30% increase in population, and that needs a lot of new metal or old metal to satisfy the demand. So the increasing gross national product is the other thing, and it is adding the need of metals in here. Non-ferrous metals production has been in under the loop, so to say, for the couple of, let's say, 5-10 years, and this is based on new technologies and new requirements due to the global warming. So in general, if you look at copper, zinc, steel, not stainless steel, but carbon steel, their demand is growing at the rate of 2 to 5% each year. And then we have, in addition to those kind of old metals, we have new technology metals like gallium, indium, tellurium, which have much higher growth rates. And part of this comes from those new technologies, as I said, but also from the general trend of changing from fossil energy to renewable energy. And that is perhaps the reason why this forecast 10 years from now proposes nickel consumption double of that what was consumed 4 years ago here. So it's the green electricity which needs conducting wires primarily in electronics and high voltage systems. It's copper, but in many other uses, aluminium. And then the battery, car batteries, which is seen here. how we estimate or evaluate the kind of trends of societies, how those societies are consuming metals, which is rather tricky task. And World Bank and also United Nations have taken this kind of term in to assist that evaluation. It's not very kind of well-behaving measure, but it is telling how the technological and technical level of a nation consumes metals. These such intensity of use graphs have been published already long time, perhaps 40, 50 years, and it is typically expressed in this kind of form that it's intensity of use. So it's metal utilization per people, per head, as a function of gross national product. And because of exchange rates, these may fluctuate somewhat. So we can see this kind of odd behaviors. But so this has been explained, when the kind of technological advancement of a nation has reached certain level, this intensity of use curve starts declining. So that has happened in Japan in case of steel, Canada, China, OECD Europe. But these are available for copper, for manganese, for nickel, and so on. Yes. So, as I said, it is not exact and well defined in such a way that the intensity of use would be easy to estimate in certain cases where the inflation and other financial issues are present, but it is perhaps the only way to estimate how nations, not individual persons, but nations are consuming. And this is in wide use in as a tool for making estimations for the future. availability of energy is one major thing is in metal making, and as I said earlier, so in normal times, except in very short periods of time, metals cannot be cheaper than the energy involved in their processing or smelting. And now when we are very much concerned about global warming and its major origin, the carbon dioxide footprint of an operation, that carbon dioxide footprint must be taken into account. So it in the future, this CO2 footprint may limit the use of metal in certain application and supports development of substituting materials in those end uses. So this example, which is shown here in these three graphs, is a very long-term estimation on availability of nickel energy price in smelting of stainless steel, and then the standard grade, probably 308 or 316 stainless steel market price development, and the time span here is huge. So it ends up in 2250, so more than 100 years. And we can see that these researchers have estimated the energy price going up quickly after probably 2040 or something, and at the same time nickel availability and availability to stainless steel making is going down. So that means that 75 years from now, standard stainless steels are not much more expensive than now, probably double or triple. But after 2100, there will be major increase in price, and that means that today stainless steel industry is developing low nickel grades, high manganese grades, instead of the current qualities. This is rare forecast, and we can understand that this cannot be accurate, but it it gives a nice indication how two major components of stainless steel making, so energy and nickel, how they have impact on the price of stainless steel. Much more and much shorter term worry is now on actual nickel and cobalt availabilities. For electrification of the societies, and that means that cobalt, which is very small metal by volume, and nickel, which is produced perhaps 2.5 million tons a year, there is indication that cobalt is first consumed in such a way that it has kind of cobalt resources have difficulties in satisfying the supply, the demand. Sorry, and that means that also this cobalt and nickel based battery chemistries will not last long. This is European Atomic Energy Community estimate already on 2018, but their forecast said that we will see troubles in cobalt supplies by 2030, so 6 years from now. So those of you who have decided to work with batteries and battery chemistries, so there will be a very intensive work period for you to develop something which is cheap, like these phosphorus ion systems, but also effective, like these lithium cobalt nickel chemistries. Then there is one major problem in our horizon. In many cases, like stainless steels and these battery chemical chemistries, we can hope at least that there is substitute coming for a certain recipe. But if we need to transfer electricity effectively, that means that we need copper and pure copper. So 99.99% pure copper. And there is no substitute for that. Well, silver has slightly better conductivity than copper, but it's not available so much that it could act as substitute for copper. All right. My last slide today will give you the recent forecast by NASA about sea level rise scenarios some 100 years ahead. And that means that when the sea level rise after 100 years, one scenario says that it will be about 30 centimeters. The other scenario says that it will be double. So this is very bad thing to those countries which are on islands and those countries who can't resist sea level rising half a meter or so. And that means that we need to really be concerned about the release of CO2 in our atmospheres. It is the key. And if we end up with that global warming in the melting of continental ice in Greenland, that rise to 2100 will be more. So then large areas of seashore countries are losing their areas, and perhaps at least those countries that kind of metal shortages are less a problem than the ocean level rise. Thank you very much. This is this end of my first lecture, and here you see the contact websites of Aalto University in case you would be interested in studying on master level or doctoral level in Otaniemi campus.
Thank you, Becca. So everyone, I have a time now. We have time for questions. One questions first. If we have still a time, we can move to the next questions. So please don't be shy. You can ask anything to Pekka regarding sustainability and metallurgy. So you can raise your hand and then ask question. Okay, Ahmad Fadel, please. You can unmute. Yes.
Right, thank you. Thank you, Pekka, for your crystal clear presentation. Really interesting. And I've got one question on the topic related to this. What do you think holds us back from recycling end-of-life goods, whether in the policymaking or technological limitations? So, what is holding ourselves back for now? That's all from me. Thank you.
So you mean that when recycling metals, so
yes, recycling. You ask
so
about, can you type because your voice is not clear? It's like cut off and yes.
no, the line was not good. So if you're recycling metals, I understood that you asked about what is more important, technology or the legislation. Was it so? Yeah, to my mind, it is legislation and whatever the government is. So what your government is seeing necessary to enable collection of end-of-life goods, to enable the use of reuse of those end-of-life goods, to enable all this circular economy, which is evidently a good thing for the metal making society, so that we are not so fast consuming or of all of our mineral resources. In Europe, we have different type of legislation from US, and in many countries in Europe, we have included in the sales price, we have the recycling cost. So if you buy a car and you use it so long that it's not anymore allowed to go to the streets and roads, so you can take it free of charge into the recycling center of cars. Or if you buy a car battery, lead acid battery, its price includes recycling fee. You take it back into the garage you have bought it, and they organize its recycling to a legal kind of recycling facility, which is not here in Finland, but it's in Sweden. So yeah, these must be organized legally, and if you have my example at what did you do with a AA battery you bought from a shop, and once it's dead and it's not rechargeable, so your your next step is either to scrap it into your waste, or take it into some place which has free recycling collecting system. And they are in this country, they are in all shops selling electronic goods. So if you don't have that kind of legislation, very few people cares to do that. And that means that they don't understand that it's important. But if there is some incentive in that, so perhaps that awareness will be higher, so to say.
Okay, guys. I hope that can answer the question. Next, one more. You can raise your hand and I will select. Okay, Billy. Okay, it is answer more than my question. Kitos PK. Okay, Kitos. Kitos is thank you. Okay, Billy, please open your mic.
Thank you for the opportunity to ask Professor Pekka. Let me introduce myself. I'm Billy from Metallurgical Engineering ITB, batch 2021. I want to ask about the demand of green energy transition, and on the other side, we also had the demand in the minerals in the futures. So as it is known that the demand for several minerals such as cobalt or such as steel will increase in the future. On the other hand, the process of producing these metals is not yet sustainable, still in process, such as hybrid and Sweden. But on the other hand, there is a demand to make a transition to a green process and circular economy. In your opinion, what is the strategy for industry players in preparing for this? Thank you.
Yeah, that is actually topic of my tomorrow's lecture. But yes, we have that kind of situation in metals industry that steel is produced some 1,800 million tons per year. And they are the biggest CO2 source in the world. Second biggest is perhaps the cement industry, but it's not as big, but close. And many steel makers have been examining and piloting even carbon-less steel making, meaning that no carbon is used in the ore reduction. So from hematite to metallic iron. And it's not only the Swedish hybrid, but it's all major steel makers, Tata and the other steel companies. Steel industry is such a huge volume industry that it takes long time, even if those measures would be taken now. So SSAB, which is building the first hydrogen-based, they don't call it yet full-scale production plant, but some kind of demo plant. It's still perhaps 1 million tons of steel per year. And it should be finalized 3 years from now in Sweden, northern Sweden, Luleå. And that has been preceded by probably 10 years piloting and planning and engineering design phases. So SSAB has a capacity of total capacity. They have 2 blast furnaces in Finland, 2 or 3 in Sweden. So that 1 million tons is perhaps 20% of their production. And it takes tens of years to convert these iron making furnaces into furnaces which are using only hydrogen. And then we must remind that there are metals which are produced with carbon, but hydrogen is not strong reducer enough to make that reduction. So something else must be there used like ferrochromium smelting, ferromanganese smelting. They rely on carbon because it's powerful enough for that oxide. But luckily they are rather small industries in comparison with steel industry. Yes, this is the big dilemma in metal making. It is not non-ferrous, which is not producing carbon dioxide practically at all, but it's the steel making industry which is very, very big polluter of CO2. I hope I gave some answer to your question.
Okay, Billy, is it answer your questions? I hope so. Okay, everyone, now is the time, and don't forget to fill the attendance today, and we will email you to join to the WhatsApp group. So all information, including how to access to EduNext and when is the deadline of the assignment, will be informed later. So see you tomorrow, and thank you, Pekka. Bye bye.
Thank you. Bye-bye.
Thank you, Pekka. See you tomorrow.
See you.